Welcome to 16.4, where we're going to introduce Green's theorem, which is one of the pillars, kind of the three big pillars of vector calculus. Green's theorem, Stokes' theorem, and the divergence theorem. So Green's theorem is a formula in 2D, and it does a very peculiar thing. What it does is it relates the line integral around the boundary of a region. So here we've got this curve C that is closed, does have to be closed, and wraps around some region. And it relates an integral around the boundary to an integral about in the interior of the region. Specifically, by the way, when we talk about going around the boundary, there is a right and a wrong way to do it. Typically, what we mean is when we go around the boundary, if you go in a counterclockwise direction, that is, in a direction that we would consider to be commensurate with the right-hand rule, we consider that to be a positive orientation. And if you go the other way around a curve in the clockwise direction, we would consider that to be a counterclockwise, a negative orientation. So what Green's theorem actually says is it says, let's say you want to do a line integral around some closed curve C, and we're going to use that little circle to indicate that it's a closed line integral. P dx plus Q dy. You want to do some line integral of this form. Assuming that that line integral is positively oriented, if C is positively oriented, then we make this claim that the line integral around the boundary of the whole region is actually equal to a double integral over the region enclosed. And specifically, the double integral that we get is the partial derivative of q with respect to x minus the partial derivative of p with respect to y. So this is qx minus py dA. So this is a really powerful formula because it basically gives you a choose your own adventure. Which would you rather do? Would you rather do the line integral, or would you rather do the double integral? So as an example, this is the same example from your book. Let's say we were looking at a little triangular region, and we want to go from the origin out to 1, 0, this way up to 0, 1, and then back down to the origin. Now, let's say I want to do this particular line integral. I would like to do the line integral over that whole boundary of x to the fourth dx plus xy dy. Now, certainly, I could calculate this line integral. It wouldn't necessarily be that difficult. One thing that I would have to do, though, is I would have to actually do 3 line integrals. I'd have to parameterize each of these 3 separate curves, these little line segments, and then add up all the resultant vectors, parameterize each one, put them in terms of dt, and then add up all 3. Green's theorem gives me an alternative. It says instead what I could do is I could look at P and I could look at Q, and I could turn this into a double integral instead. And the double integral over the region enclosed would actually look like qx minus py. So when we take qx, what we will get is we'll just get y. Py, in this case, turns out to be nothing. So we just get y minus 0. And if we complete this, right, this is the double integral of y, and then we could just go ahead and set up dy dx 0 to 1 minus x, 0 to 1. And I think we can agree that we would much rather do this one than this one. It's much simpler and helps us out a lot. Now, there's other applications of Green's theorem. Sometimes we want the double integral, other times we want the line integral. So there's another application. We can recall that if I want to find the area of a region, all I need to do is do the double integral over that region of 1 dA. The question is, can I turn this into a line integral? And the answer is absolutely yes. As long as I can find a qx minus py that's precisely equal to 1. And it turns out that there's a bunch of different q's and p's that do this. You could have, for instance, p equal to 0 and q equal to x. You could have q equal to 0 and p equal to negative y, and so on and so forth. Your book actually provides a couple different options for this. But our favorite ones are kind of listed here. So I'm going to switch colors. So it turns out that the area of the area of something, you can actually calculate by doing an integral around the boundary. So you can actually do one of the following line integrals around the boundary. So you can do x dy. You can do negative y dx. You can also do 1/2 of kind of the sum of those of x dy minus y dx. Basically, any combination of q and p that lead you to qx minus py being equal to 1, the double integral around that boundary will actually give you the area of the region. And I'd like to show you a little test of this. So what we're going to do is we're going to calculate, we're going to use this to calculate the area of one arch of a cycloid. So this is kind of what a wheel does. And in this case, we're going to parameterize it this way. X equals t minus sine t. Y equals 1 minus cosine t. And this goes from 0 to 2 pi. Now, you can do this as a function, y as a function of x, but it's not very pretty. Actually, there's places where you can't do it as a function, so it's just not very pretty. It's got some cusps in it. So what we're going to do is we're actually going to find the area in one arch of this. And the way we're going to do this is we're actually going to take a line integral around the boundary. And what we're going to do is we're going to go out this way. And we are going to come back this way. We're going to come back this way. Now, in this case, you'll notice that our boundary is backwards. Actually, I should have done it the other way. I should have us going the other way to keep us in the proper right-hand rule orientation. So pretend we are going the correct way around this. We're actually going this way around our thing in the proper right-hand rule orientation. So I want to calculate my my line integral around this. And just for the sake of argument, what I'm going to do is I'm going to choose this one. Oh, I remember why I actually drew it the correct way. So I actually was right the first time. We're going to go backwards around our loop. The reason we're going to go backwards around our loop is it's easier to calculate the line integral for increasing t. So what I'm going to do is I'm going to take this negative y dx, and I'm just going to take off the negative sign. Because that's what Green's theorem lets you do. If you use the negative orientation, you just get a negative answer. So I'm going to calculate this integral, y dx. This is the line integral for this region. And in this case, I'm going to choose this. You could choose something else. I've tried it a couple different ways, and this turns out to be one of the easier integrals to do. So in this case, I know that y is equal to 1 minus cosine t. And in this case, if I take dx here, I also get 1 minus cosine t dt, and that's going to go from 0 to 2 pi. Now, to be fair, this is actually only C1. This is actually only C1. It's going to turn out that the line integral along C2 is exactly equal to 0. And the reason it's exactly equal to 0 is, well, what's y equal to everywhere along C2? It's equal to 0. So the bottom part actually doesn't contribute anything to our line integral. So in this case, I can go ahead and calculate this. I can FOIL this out, 0 to 2 pi. This is going to be 1 minus 2 cosine t plus cosine squared t dt. When I go to calculate this, I can take my integral. This will give me t minus 2 sine t. And by looking it up in my table of integrals, cosine squared t gives me t over 2 plus 1/4 sine of 2t. This is from 0 to 2 pi. And when I plug this in, what I get, I'm going to extend it over here, is I get 2 pi minus, well, sine of 2 pi is nothing. T over 2. Sine of 4 pi is also nothing. And you're going to find when you plug in 0, you actually get 0 for everything here. So my answer ends up being 3 pi, which is the correct value for the area enclosed in one hump of the cycloid. So Green's theorem is a really useful thing. We're going to see lots and lots and lots of applications for it. But basically what it does is it lets you choose which do you want. Is the line integral easier? Or is the double integral easier? In some cases, you're going to be opting for the double integral. And in other cases, like for area, sometimes it's easier to actually do the line integral instead.